the day, and when the lights go out, we make shapes while we sleep, because we're always dreaming about lines, lines, circles, circles, squares, 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 triangles, triangles.
In this video, we'll finally give a proof of the fundamental theorem of algebra. So just to recall, what does this say? It says that every f of x in C bracket x of degree n has precisely n roots in C counted with multiplicity. That every polynomial with complex coefficients splits completely into linear factors in C bracket x. This is equivalent to saying that C is algebraically closed. So it may seem that the following statement is a little weaker than what we need to prove, but we've seen in our discussion of what it means for a field to be algebraically closed that it's enough to prove that every polynomial in C bracket x of degree at least 1 has a root in C. Because if your polynomial of degree n has one root in C, then it has a linear factor. And then what you have left over is a polynomial of degree n minus 1, and that has a root in C, and so on. Okay, so the first big idea is that it's enough to consider polynomials whose coefficients are not in C, but actually in R. So we need only prove that every f of x in R bracket x of degree at least 1 has a root in C. Okay, so why is this true? So the idea is we're going to think of f of x and f bar of x, the polynomial that we get by applying complex conjugation to the coefficients of f. We're going to think about these two polynomials together. And the key observation is that if f of x has no root in C, then f bar of x also has no roots in C. Okay, so why is that true? When we apply complex conjugation, it'll take a root of f of x in C to a root of f bar of x in C, and vice versa. A root of f bar of x gets sent to a root of f of x. Okay, so now let's consider this product of f of x times f bar of x. The coefficients of this product are fixed by complex conjugation. The coefficients, if they're fixed by complex conjugation, they're fixed by all of the elements of the Galois group of C over R. So what does that mean? That means that these coefficients are in their elements of C, but they're in the fixed field of the entire Galois group, which is R. So these coefficients are in R, and this product, f of x times f bar of x, is in R bracket x. So all we need to prove is that this product has a root in C. Okay, so the next big idea is that we're going to argue by induction on the degree of this polynomial. And the induction isn't going to work in the most obvious way, where you go from degree n to degree n plus 1. Instead, what we're going to do is let n be equal to a power of 2, 2 to the k, times some odd number. And we're going to induct on k. So the base case is k equals 0. So what are we saying in this case? We want to show that every f of x in R bracket x of odd degree has a root in C. But what we're actually going to prove is something better, that every f of x in R bracket x of odd degree has a root in R. And the idea is, okay, you write out. So it's enough to think about monic polynomials, because you can always scale the polynomial by 1 over the leading coefficients without changing the roots. So let's take our polynomial x to the n plus an minus 1, x to the n minus 1, plus a1x plus a0. And you can see that when x is very large, much larger than 0, because the x to the n term is so much bigger than an minus 1, x to the n minus 1, no matter what this real number is, this polynomial is going to evaluate to something positive. Similarly, when x is very, very, very negative, the x to the n term will be very, very, very negative because n is odd. And there's no way that the rest of this polynomial can make up for this very, very negative term at the beginning. So this will be less than 0. So you have some continuous function that evaluates to something positive at some point and something negative at another point. So by the intermediate value theorem from calculus, it has to cross from being negative to being positive somewhere, and it has to take a value, have a value that is equal to 0. Okay, so what are we seeing? We're seeing that in the case that the degree is odd, f of x in R bracket x not only has a root in C, but has a root in R. So that proves the base case, k equals 0. Okay, so I'll pause and erase. And first, I'll say something that the base case gives us about extensions of R. And then I'll show the main idea that allows us to prove this result by induction. Let's continue our discussion of the base case of this result. We've shown that every f of x in R bracket x of odd degree has a root in R. This means that there are no non-trivial odd degree extensions of R. Why? If there were such an extension, it would be a finite extension of R of odd degree. And by the primitive element theorem, we could write this as R adjoin alpha for some alpha, where the degree of the minimal polynomial of alpha is the degree of the extension. So the minimal polynomial of alpha over R has odd degree. But now this is an odd degree polynomial with coefficients in R, so it must have a root in R. But we also know this is irreducible in R bracket x. So the only way that this polynomial that has a root in R could be irreducible in R bracket x would be if it was degree 1. Okay, so that's all I want to say about this base case. Let's move on to the general case, where n is equal to 2 to the k times m, where m is odd. And now we want to suppose that k is at least 1. Okay, so f of x, this polynomial, it has n roots in a splitting field over R. Let's name those roots. Let's call them alpha 1 up through alpha n. And one key idea is going to be to consider the field k, which is generated over R by these roots and also by I. Okay, so k over R is a Galois extension, and C is contained in K. So it's you adjoin alpha 1 up through alpha n, which is a splitting field over R of this polynomial f of x, and then you also adjoin I, which is a root of this polynomial x squared plus 1, which is in R bracket x. So you could take this product of f of x times x squared plus 1 and see that this is going to be the splitting field of this polynomial. So it's a Galois extension. Okay, so the big idea is going to be that for any t in R, you can define a special polynomial. So if I were to describe how this argument works, this proof of the fundamental theorem of algebra, one big idea is to first show that you can restrict to just considering polynomials with coefficients in R. Then you have to remember this idea of doing induction on the degree, where the induction is on the power of 2 dividing the degree, rather than just the degree goes to degree plus 1. The third big thing to remember is, what are these polynomials? So if you remember what these polynomials are, then I think you can remember the rest of this argument pretty easily. Okay, so for each t in R, we're going to define a polynomial Lt of x. So it's going to be defined as a product over all pairs I less than j of x minus alpha I plus alpha j plus t times alpha I alpha j. So we're defining this polynomial by describing its roots. For each pair I and j, it's going to have a root alpha I plus alpha j plus t times alpha I alpha j. Okay, so why this polynomial? Well, we have this Galois extension, k over r. And any element of the Galois group, any sigma that's an automorphism of k fixing r, has to permute the roots of this polynomial f of x. So it has to permute alpha 1 up through alpha n. So what does that do to a term like this? Well, if you permute these alphas, it's going to send each term that looks like x minus alpha I plus alpha j plus t times alpha I alpha j to another term that looks like this. So it's just going to permute the terms in this product here. Okay, so if you just permute the terms in the product, you fix the whole product. So that any automorphism of k fixing r fixes the polynomial Lt of x. So what does that mean? That means that every coefficient of this polynomial is fixed by every element of the Galois group of k over r. So each coefficient is actually in the fixed field of the entire Galois group, which is r. So Lt of x is in r bracket x. Okay, so what do we know about this polynomial? It's in r bracket x. What is its degree? Its degree is the number of pairs I and j from 1 up to n, where I is less than j. So what are we doing? We're just choosing two elements out of a set of n elements. So the degree is n choose 2. It's n times n minus 1 over 2. What is that? Well, n is 2 to the k times m. So it's 2 to the k minus 1 times m. That's n over 2. And then what is n minus 1? It's 2 to the k times m minus 1. And the point here is this is odd. So what is the power of 2 dividing n choose 2? It's 2 to the k minus 1. So this n choose 2 is of the form 2 to the k minus 1 times m prime times some odd number. So by induction, remember the induction is on this power of 2, Lt of x has a root in C. Okay, so I'm going to pause and erase, and I'm going to tell you why Lt of x having a root in C is going to lead us to the fact that f of x has a root in C. We know that for each real number t, this polynomial Lt of x has a root that's in C. What are we going to do with that? Well, we know the roots of Lt of x in this field K. We know that they look like alpha I plus alpha j plus t times alpha I times alpha j. So what this is saying is for each t, one of these terms, for some pair I and j, we get something that's actually in C. Okay, so we can vary over all of these infinitely many choices of t, and for each one, we get some pair ij for which this term is in C. There's infinitely many choices of t, but only finitely many choices of I and j. So that means that there have to be two different choices of a real number, let's say s and t, that are not equal to each other, for which for the same I and j, we get alpha I plus alpha j plus that real number times alpha I alpha j is in C. Okay, so what are we seeing? There must be some pair I and j and some s not equal to t in R where alpha I plus alpha j plus t times alpha I alpha j is in C, and alpha I plus alpha j plus s times alpha I alpha j is in C. So if you take the difference, then you know that t minus s is a non-zero real number, so you can divide by it. That shows that alpha I times alpha j is in C. Let's call that B. And once we know that's in C, then taking a difference, we can see that A, alpha I plus alpha j, is also in C. And now what we really want is that alpha I and alpha j are in C. What do we know about alpha I and alpha j? These are the roots of the quadratic polynomial x squared minus ax plus b, which is a polynomial in C bracket x because a and b are in C. I mean, you can just take x minus alpha I times x minus alpha j and see that this is true. Or you can apply the quadratic formula and see these are the roots. So what do we need to do? We need to show that alpha I and alpha j are actually in C, given that the coefficients of this polynomial are in C. And we'll do that by proving that quadratic polynomials with coefficients in C have roots in C. That just because we know that x squared minus ax plus b is in C bracket x, that means automatically the roots of this polynomial are in C. So what is that equivalent to saying? Equivalently, there are no non-trivial quadratic extensions of C. Yeah, if there were a non-trivial quadratic extension of C, then it would be C adjoined something where the minimal polynomial is a degree 2 polynomial in C bracket x that's irreducible. The roots are in this extension, but not actually in C. So what we're saying is that every degree 2 polynomial in C bracket x factors into a product of linear polynomials in C bracket x. So this is the same kind of idea as showing that C is algebraically closed, but only for the case where the degree of our polynomial is 2. Okay, so by a change of coordinates, completing the square, we need only consider polynomials where the linear term is 0, x squared minus alpha, where alpha is in C. Okay, so what do we need to know about alpha? Alpha is a plus bi, where a and b are real numbers. And we just need to show that alpha has a square root in C, that there's some complex number that you square it and you get the complex number alpha. So there are two ways to do this. I think the easiest way is to just write alpha in polar coordinates. Alpha equals r times e to the I theta, where r is, let me say, greater than or equal to 0. And theta is between 0 and 2 pi. It can be 0, but not 2 pi. So what is a complex number that squares to alpha? Take the square root of this real number, by which I mean the positive square root of this real number, times e to the I theta over 2. Theta over 2 is now also between 0 and 2 pi. This is a complex number that squares to alpha, so it's a root of this polynomial in C. The other root is the negative of this number that squares to alpha, and that's it. So given that quadratic polynomials of this form have roots that are in C, you can see that a general quadratic polynomial also has roots that are in C. So there's another way to do this that you can see the details in Dumb It and Foot. It's a little exercise to find what are real numbers C and D such that C plus DI squared is equal to A plus BI. So you can solve for C and D in terms of these real numbers A and B, and I'll let you think about that. Okay, so let me summarize this argument, because I think that this is, one of the big results of this whole course. What actually happened is big idea that you restrict only to polynomials with real coefficients. You do induction on the degree, where the induction is really on 2 to the k times m, where m is odd. That's the degree. So the induction's on this k, this power of 2. And then the big idea is remembering to think about these polynomials LT of x, where you name the roots of your polynomial f of x, say alpha 1 up through alpha n, and you define these polynomials LT of x, one for each real number t, by describing the roots. They're of the form alpha I plus alpha j plus t alpha I alpha j. And then, okay, what can you say about this polynomial? You can show that its coefficients are actually in R, and then you can compute its degree and see by induction that these polynomials have roots in C. And now, just by counting infinitely many t, finitely many pairs I and j, we can see that there have to be to elements that look like this that are actually in C. And now we're almost done. And we get down to the case of quadratic polynomials.